Dear colleagues, I would like to present you a scientific paper with the name Modeling the Basis Power in the Systems for Continuous Transport of Fluids and Bulk Materials. The paper starts with an introduction section. The subject of the introduction is to justify the novelty of the research. In this connection, we studied the research background. Currently, there are several models to determine the useful part of the consumed energy. In many cases, the efficient part is assessed using the no-load condition, which leads to evaluation inaccuracies. Other approaches are focused on the ratio between the energy spent per unit of product, volume, or other quantity directly related to production. Some papers examine the efficiency of the machines with water lifting applications. The research topic is also addressed in providing overview of the methods for developing better corrective measures for energy savings or how losses in metallurgy can be reduced. Other studies are focused on how the estimated maintenance of the facilities supports energy losses. The aim of this study is to offer a model of the fully functional, useful power in the systems for continuous transport of fluids and bulk materials, allowing deeper and more functional analysis of the energy efficiency by physically based decomposition of the consumption in useful and non-useful component. This paper proposes a new classification of the pointed systems. The systems are divided into those of first and second type. Type 1 systems are those where the load transport parameters, like speed and pressure, are not considered. The type 2 systems are required for a certain load, speed, or pressure. The classification is presented on Figure 1. Gravity-based mathematical models are developed for each kind of transport system according to the presented classification. The main energy efficiency evaluation criteria is proposed towards the potential energy of the mass of the load. The models are shown on this slide. A case study is conducted in order to investigate the applicability of the developed models. A powerful pumping system for water feeding of a steam generator in a thermal power plant has been selected as a case study object. According to the proposed classification, the investigation object is a Type 2 lifting system for continuous transport of fluids. The pump is driven by an induction motor with a rated voltage of 6 kilovolts, rated power of 2 megawatts, and efficiency 96%. The results are obtained using methods described in our previous publications. The obtained energy efficiency indices are presented in Table 1. From the value of D1 equal to 1.23 and the relatively low value of A6 index, a satisfactory structural perfection of the pump is shown. Based on the coefficient D2, it can be concluded that there is an opportunity to improve the operating conditions of the pump by additional loading until it reaches the optimal level. This improvement can lead to savings of nearly 180 kilowatt hours for a period of 67 minutes. This paper proposes a new way to determine the theoretically necessary electricity consumption by a basis power modeling method. The method developed in this study allows to identify clearly and precisely this minimally needed energy and to compare it with the consumed amount. This gains a better understanding of the total losses. The example with the pumping system above shows that approximately 30% of the energy is lost. This makes clear that there are significant possibilities for optimizing the systems. Conclusions. A new classification has been developed for bulk materials and fluid transport systems, by which the system type can be determined. An aggregate model, including 9 mathematical expressions, is derived, by which, after determining the type, the required minimum possible power can be accurately calculated and compared with the total consumption. The model can be used both in existing systems and when designing new ones. The proposed methodology is demonstrated in a real working environment by revealing the basis power for a rising system for continuous transport of fluids of type 2, part of a steam power plant. On the basis of the proposed model, it is possible to plan optimizations of the systems environmentally and economically. Future research covers algorithmizing of the model and developing relevant software products to computer-aided research, justification of the applicability of the model to the rising, horizontal, and descending systems for continuous transport of bulk materials of type 1 and type 2, as well as to the type 1 fluid systems. Thank you for your attention.